Hi, Prof. Good evening, and thank you for this time, and thank you for letting me do this assignment over this week, these weeks. I am also want to say that I'm doing very well at my work because I have this time for doing these assignments. Otherwise I'd be very hard pressed at work too. So, yes, Prof. So we're discussing Heaps versus BST, and I did do a little write up. As usual, I've evaluated Heaps versus BST. I'll just go through this. The first thing I want to say is that um, um, the concept of heaps is midway between a random sequential insert and a totally organized BST. So the BST is like the most organized structure we can find. So heap is like an in-between method of storage. Okay, let me share my screen so I can show that to you. Yes. So I wrote a little write up about what I discovered while coding for Heaps versus BST. The first thing is inserting. The binary search tree first tries to find the spot in the tree and then inserts, whereas the heap inserts at the leftmost child first. There's no rebalancing here, but the heap works its way to rebalance the tree and does sync or a float. And here the work is done in conditional checking before insert. Here there's a lot of effort to rebalance after each insert. Searching wise, min search and max search involves traversing the entire tree. Whereas here the min or max search is easiest and has a computation of one. It's instant to find the min and the max depending on our heap. The random search for this is perfect. And the BST is built for random search. Whereas in a heap, the random search is very difficult. To do a random search is absolutely costly. And then the first node remains the root node forever in what do you say, in a BST unless it's deleted. Whereas here, the first node is the root initially. However, rebalance occurs after each insert, so this may not be root forever. What is the purpose? Heap is an in-between method of storage between totally random sequential inserts and extremely organized BST. Oracle database by default uses heaps as the method of storage of a table unless the primary key is specified, but then it uses an indexed organized table, or that's a tree, and the rows are at the leaves of the tree. Um, yes, deletion of an item does not call for rebalance in a BST, whereas here the pop uses float rebalance, or say sync, yeah, for deletion of min max node. And I was just thinking, the BST can be a min and max heap simultaneously. All you need is a pointer to the minimum and maximum value. Then then the BST would be exactly like a heap and with more value, because now you can search, you can find the min value in a second, you can find the max value in a second, and you can retain the values. Why do you have to throw away the value? You may need it for something else, but as long as you know what the max or min value is, the heap has served a triple purpose. Then I came to know the heap queue library in Python is an array and list implementation and does not use linked lists or pointers. So that's bad because the implementation is very based on an array, and this implementation is um, it's not robust, because it depends on the array indexes for the computation. Whereas here, when we implemented pointers, it's very difficult. So I had to create several new pointers. I created a pointer called parent. So not only are you going from top to bottom, you're also able to go from bottom to top and trace the entire lineage of the child right up to the root node using parent. And there's another concept that's leftmost. We need to swap, when we delete, we need to swap the root with the leftmost node, and that I've already created a pointer ready, and you can evaluate the leftmost node at any time, and that makes it enable easy to swap out both these values. So I created these extra pointers, and yes, I need to hot swap. And yeah, to delete element, you need hot swap, the leftmost on the root. So I create an extra pointer. Oh yeah, a third pointer called hot swap to track the sync movement. Yes. Then you need to evaluate both children, and you need to evaluate the leftmost node again. So let's go straight and rough. Yeah, right. I'm very scared that the sharing is not turned on. Otherwise my effort will be in vain here. Okay, Prof. Here we are. So I'm going to show you a little bit of the code via heap.py. As you can see, yes, we're importing DQ, but that's not our real DQ. That's actually just for evaluating the breadth first search. So that's not our DQ. And here in the tree, if you can see, I've added a few more pointers. I have root node. I've added a new pointer called size, a new variable called size to track the size of the heap. And also I have another one called leftmost to point to the leftmost value so that the down sync is very easy. Down heap is very easy. Now insert. So I have this insert, and but actually I created a better version of that insert, and that is called a breadth first insert. So this is what the breadth first insert is: a combination of breadth first traversal and insert, because I realized uh, to go and track the leftmost nodes and to traverse across the same height, I needed a breadth first traversal. So this is what it does: it takes the first root node, and if it is none, it adds it. It increments the size also, and leftmost equal to node. Next, it evaluates if the size of the tree heap is in these values. So if it is, the heap is complete. That is, we've moved all the way from the left to the right, so that height is complete. Now we have to go right to the leftmost child. So I've created another computation for that. We can make this um, as an real-time computation, but for now I just let it go so that it's quick to evaluate. Then current equal to left root node, while this is tripend equal to this, current equal to this. So now it swaps, it inserts into the leftmost node, or on the next level, leftmost leaf actually. Then here we have another one, traversal Q. Okay, now this one is to print the length of the traversal queue, and it goes breadthwise, and then while this is equal to this, it evaluates, it pops out the left, and this is called NFQ. That's the node from Q. That's different from the node that we just got, and pops out, and here it is. And that's now the DQ is very, very complex. The DQ is tedious, but it's not as complex as BFS. So this is what we present: the topmost value of the queue, and then we check if the node equals to leftmost data. Then we delete the leftmost swap node and evaluate if it's a right or left child. And then we say right child is deleted or left child is deleted. Now we start with that. We evaluate the children. You can see the coding, how much coding. It's very tedious. This coding is, it's not too intelligent coding, but it's very tedious, because you have to evaluate both the left and the right child to evaluate, you just can't evaluate one child, we have to evaluate two. So then we say the hot swap is at the leaf, perfect, so no more children. Else if um, both of them both children are here, you check for if it's greater than the left child, then we swap this, we swap with left child. Then if both the children have values that are not satisfying the heap, then we have to evaluate which one is not satisfying the heap more, and that value we're going to swap. So if left has a greater difference, we're going to swap with the left child. Or if the right has a great difference, we're going to swap to the right child. And that's how we do it. And I also create another function called evaluate leftmost, because with the leftmost value is very critical to the evaluation. So even after you do a DQ and you go through all the values, and you swap out and do a down heap, we have to do a leftmost evaluation. So I wrote that again, this other function to do that, you know. And so it's very tedious. But without that, we'd have to compute the leftmost value every time we do a DQ or every time we do an insert. So this really helps us a lot. Then we have breadth first traversal. I've left that code here. Here's the main one. So they're just four things: load CSV, display for breadth first traversal, DQ by priority exit. Yes, so the same minute, but very few items. And then I do r4.csv. Perfect. So it shows the length of this. So then it shows stepwise. It took 4 and it put a new element in this. The heap is complete. That means it's ready with the value 4 and it's going to insert it at the leftmost child. Then it took 7. Then it did 5. Then it says the heap is complete, insert leftmost, then goes to all these 4. So display L2 2. Perfect. If you do 2, length of traversal Q is this, height is equal to this. At height 0, value is 4. At height 1, you have this. At height 2, you have these, and all these are leaf nodes, Then list it, list it, list it. Perfect. Now you do a DQ. Perfect. So this is very interesting. By priority. So this is what I'm presenting: the topmost value of the queue. Right child can be deleted. So the right child can be deleted. So then it says the hot swap is at the leaf. So no more child. So 4 was interchanged with 9. Yeah, 4 was interchanged with the leftmost, which is 9. And 9 is at the leaf, so nothing more. So it removed it and took it out. So if you want to see what happened, press 2, and it says that 4 is no longer here. Height 5, 7, 6, do this, and leftmost. Now we do another DQ, and we do another, and again it took, which one? It took 5, leftmost deleted. These my children, these my children. So again I display. Okay, yes, here I'm display, and so it shows now the leftmost is 8. So this is your height. So at height 0, 6 is there, 17. And I do once more. And that's the function. So that's how it is. And so that's how we do it. But it's very tedious, prof. And there is a lot of advantages to BST, but I feel the heap is it just provides the largest and the smallest value, but for all the rebalancing, for all the down heap and up heap, I don't think it's worth it, prof, to have a structure called heap. But if you want to make it better than sequential inserts, if it's a better option than sequential inserts, then yes, it is. But instead, we could have a BST that also has a min pointer and max pointer, and you're getting three functionalities in one shot. So that's my take on this, prof. And I want to thank you once again. Thank you so much, prof.